In this video, I'll talk about electromotive force, terminal voltage, and internal resistance. Although this sounds like some force, it is not a force, and I'll explain what it is. All the terms, electromotive force, the terminal voltage, and the internal resistance, all these terms are related with a battery. So when you go and purchase a battery or a cell, it does say like 1.5 volt or 9 volt. That is the EMF, that is the electromotive force. But in fact, when you go and measure the potential difference across a battery, okay, if you have a voltmeter and if you measure the potential difference across a battery, it would always read a smaller than 9 volt battery or 1.5 volt battery. Why does it show a smaller than 1.5 volt or 9 volt battery? So all sort of things I will discuss in this topic here. So now let's talk about a battery. This battery here. A battery is made of some materials, and any material has inherently resistance. If certain thing is made of the materials, that means it must have to have some resistance. So that means a battery, which is also made of some sort of materials, the chemicals, has resistance built inside it. That resistance is called internal resistance. So internal resistance is in fact the resistance of a battery. Okay, so we now know that what is internal resistance? The internal resistance is the resistance of a battery. So that means if we have a battery, then this battery, 1.5 volt, let's say, this battery can be now think of this way. So here, this is how we can show up. So battery, now let's say this is a battery and an internal resistance here. And in this case, this is an ideal battery. When I say ideal battery, what does it mean? It means this one has no any internal resistance, and we have now denoted this one, the internal resistance, this way. Okay, so a battery without, so EMF or electromotive force is the potential difference across the battery when or which has no any internal resistance or zero resistance. Or when later I will just show that the electromotive force across a battery is when there is no current in the circuit. So this battery, 1.5 volt battery or 9 volt battery, whatever it is, can be assumed this way here: an ideal battery with zero resistance plus an internal resistance. So if you look from outside, this is how it looks like: a battery and then internal resistance. Okay, and now let's talk about this resistance here. So we have a battery and we connected an external resistance. The moment we connect the external resistance, there would be some current flowing through the circuit. Okay, there would be some current. And the potential drop, let's measure the potential drop across this one. The potential drop across this external resistance, this is an external resistance. External resistance. The potential drop across this external resistance that we measure is the terminal voltage. So whatever we measure across using a voltmeter would be the terminal voltage. That means if we connect a voltmeter here, then that would be the terminal voltage, and it would show slightly smaller than 1.5 volt. Okay, so this is what it is shown here. So there would be some current. Now take a look here. As the current is flowing, the same current will be also flowing through the internal resistance. Okay, so the potential drop here, there would be some potential drop across this internal resistance. And how much would be the potential difference across this internal resistance? You remember the V is equal to I times R. So this much potential drop would be dropping across this internal resistance, and your battery would show this much amount as smaller than this ideal battery. Okay, so and you see that the the voltage that you would measure depends upon the current in the circuit. Okay, so as smaller the current is, and we'll just talk about as smaller the current in the circuit is, the true value of EMF you will measure. So and I will explain everything again using the simulation. So let's now write down the equation for this one. So now let's measure the what is the potential drop across this one. The potential drop would be V equals to epsilon minus IR. So this is the electromotive force, and there's a potential drop across this one which is IR. So the potential drop across the V would be E minus the potential drop across this one. Okay, or simply we can also write down this EMF would be equal to I R plus R, right? So this is the net resistance, that's the net resistance, and this is the current in the circuit. And if we call the V as the potential drop across this external resistance, so the V would be simply equal, I'm just writing down here, V equals to IR. So from these two equations you can show that this equation here, V equals to epsilon minus IR. So the potential drop across this external resistance that we call the terminal voltage. And from this equation, or from this equation, or from this equation, what we can write down, the equation for the current would be epsilon or electromotive force plus R plus R. Okay. What is it written here? So now let's talk about the internal resistance. I already talked about a battery is made of a matter. So it is inherent to have some electrical resistance of it. And that resistance is called the internal resistance. Now let's talk about the electromotive force. Again, it is not a force. What it is the potential difference of a battery or source when no current is flowing in the circuit. So now let's take a look here. In this equation, if what we're doing here, we always measure the potential difference across this external resistance. So if there is no current, if the current is very small, or when there is no current, then this term would be 0, and whatever we measure would be equal to the electromotive force. Okay, so when there is no current, then the terminal voltage would be equal to the electromotive force. So electromotive force is not a physical force. It is just the potential difference of a battery when no current is flowing in the circuit. Or electromotive force is the ideal, the potential difference of a battery without internal resistance. Okay, or when there is no current in the circuit, or without internal resistance. And the unit that we call is the voltage. But remember, no battery in the universe exists without zero resistance. Okay, so but there is a way, even if the battery has internal resistance. Remember, even if the battery has internal resistance, we should be able to measure the electromotive force of it. So electromotive force, so this is the best way of defining. The electromotive force is the potential difference of a battery when no current is flowing in the circuit. And there is a technique that is called the potentiometer, through which we can determine what is the electromotive force. But using a voltmeter, using a voltmeter. So if you have a voltmeter, we always measure the terminal voltage. Terminal voltage. Okay. And the unit of electromotive force is the volt. Now let's talk about the terminal voltage here. So it is the output voltage of a device measured across its terminal or across a external resistance. That is called the terminal voltage. So in this case, when you have a voltmeter and we measure across this external resistance R, then that would give you the terminal voltage. So we know this equation here. We have this equation. I is equal to epsilon R over R. This is the load resistance or external resistance, and R is the internal resistance. So now let's try to plug in some values and see what we get here. So now let's assume R is 1 ohm, or means the internal resistance is 1 ohm, and R, your external resistance, is 100 kilo ohm. So that means this R is significantly larger than the internal resistance. In that case, I would be epsilon over R. Okay. In this case, if you measure the terminal voltage, then that terminal voltage would be close to the EMF. So here is the trick. If we want to truly measure the EMF, then you have to connect a large resistance in the circuit, and then you measure the potential difference across the large resistance. That will give you the close to true EMF. So why is that? Because if you have a large resistance and if you plug into this equation, then you see the current is quite small, and the V internal means the drop across the internal resistance is quite small. And then if you measure across the external resistance or the load resistance, it would be 9.99 volt. Okay. So what do you see here? If the external resistance is very high, then there is insignificant amount of potential drop across the internal resistance. There is not much drop, so not much power is lost. But now if R, external resistance, and internal resistance are compared, now let's say if you have your internal resistance is 10 ohm and your external resistance is 10 ohm and your EMF is 9 volt, that's what is written onto the battery, then in this case the current would be 4.5 volt. And now here I'm just calculating the power. So the power formula is I squared over R. So this is the power lost across the internal resistance, and this is the power delivered to the load resistance. When I say load resistance, it could be a light bulb. Okay, it could be any heater. And you see now, so the power that is lost across the battery, let's say the battery here, because the internal resistance is across the battery, would be 202.5 watt. What does this mean? That means the battery is getting heated up. The battery will be so hot because this much power is now losing across the internal resistance which is inside the battery, so the battery would be heating up. Okay, so almost exactly 50% when the load resistance and internal resistance are equal, then the 50% of the power would be lost across the battery itself or across the internal resistance. So this is such an important point here. Okay, so if a battery, let's say, has 5 ohm, if R is 5 ohm and you connecting 5 ohm across the battery external resistance, then 50% or half of it would be lost across the battery itself. And here I'm just making one more important point. So in general, let's say you have an ideal battery here, an ideal battery, and if we connect by a wire with no resistance, then the current has to be in fact infinite. But that's not the case. Even if we short circuit a battery, there would be some current into the circuit. We do not get infinite current because the battery itself has some internal resistance, so there would be some drop across this one, and the amount of current can be given by this formula here, epsilon divided by R, and it is not infinite even if we short circuit a battery. Okay, so now I just talked about this all this electromotive force, terminal voltage, and internal resistance using the nodes. Now let's verify this one using a simulation. So here what I'm going to do, I'm going to select a battery here, and this battery has no resistance. In fact, I'm just put one resistance here, and then let's connect an ammeter here. Okay, I'm just connected one ammeter. It measures the current for us. And then I'm going to use a resistor and then wire. Okay, so now you see the current. I'm going to use the conventional current. So let me show you. This one has 9-volt battery, and it has a 1 ohm built inside it, and this is a 10 ohm resistance. So if I measure the potential drop across this one, how much it say? It does not say 9 volt, it does say 8.18 volt. And if this, now what I'm going to change here is the internal resistance. So here I'm going to change the internal resistance to 0. Now you see this reaches 9 volt. So this is the ideal case. This is the ideal case. So if the battery has 0 resistance, then only then we measure the true MF or true electromotive force. In reality, all the battery has some internal resistance. Then you see now it has changed now from 9 volt to 8.18 volt. So this, what we measure here, is the terminal volt. The 9 volt here is the electromotive force. 1 ohm here is the internal resistance. Okay, so now let's see what happens if I increase this 10 ohm. And as I mentioned, if this external resistance or load resistance is much larger, then we'll measure close to the electromotive force. So here I'm increasing this resistance now. As I'm increasing, this is now getting bigger and bigger. 8.8, 8.9. So that's the maximum I can get to here. So you see now, as I'm increasing this load resistance, I'm getting close to 9 volt. And if I decrease this one, then I measure very small the value here. So in order to measure the true EMF, your external resistance has to be significantly larger than the internal resistance. So this is it from this lecture here. If you have any questions, write down your questions in the comment section below, and do not forget to like, share, and subscribe the channel. Thank you very much.